Very glad, even though we didn't plan it that way. I am very glad to go to have Katerina's talk and my talk together in this very exciting conference, because I will also talk, among other things, about glitches. But the topic I want the message I want to give in this talk is that you probably, from the talks I have seen, you're talking about not just to look for and find gravitational waves in LIGO and Virgo and soon Cagra data, but also how much we expect from future detectors, not just third generation detectors, but also detectors like A plus that will come soon. And when we do this, in general, you will see talks like this, and this is a plot that David Shoemaker will talk a lot more in the closing talk of this conference. So I want to talk about the experimental challenges to reach these sensitivities. Of course, in 30 minutes, and I cannot give enough, I cannot do justice to everything that's needed. So I put here a document that was put together by many members of the international community on the R&D that's needed for the next generation of ground-based gravitational wave detectors. And this is a color plot showing how much we need to how much time and investment we need in different aspects that I will talk about to get to third generation detectors. But that's only one part of it. And let me talk about that first. So this is a plot I was telling you about. And this is what I was telling, what it takes to get there, what it takes to get from where we are now. This is advanced LIGO in the last science run. What does it take to get from here to here to here? Well, it takes research on all of these things, infrastructure and facility, if we are talking about third generation detectors, core optics, coatings, cryogenics, Newtonian noise, light sources, quantum enhancements, seismic isolation and seismic suspensions, optics, simulation, control, calibration, all of that needs R&D, and I hope you are looking forward to that. But that is what we are talking about to reach those fundamental limits. These talks, these curves are all done taking into account only the fundamental, what we call the fundamental limits to the sensitivity of detectors. And just as a case study, as an example, because it's the one that I know the best, I'm talking about the advanced LIGO detectors. So in advanced LIGO, this would be the curve that we would plot. We often transform that curve into a number. The number is the range in megaparsecs to binary neutron star sources, binary neutron stars, because we have a fixed mass for black holes. That distance depends on the masses, but you can also translate it if you take some canonical masses. But this sensitivity, like the ones we had in the previous for these detectors, this curve is the sum of some other curves that are the expected noise, the expected quantum noise that now is much better understood than it was in the early 90s. And that is the sum usually characterized by shot noise and radiation pressure. But this is the total quantum noise together, seismic noise affecting us more at lower frequencies, that is how the mirrors are suspended and what active isolation we have, Newtonian noise, which doesn't have to do with a suspension, assuming a perfect suspension, how much the ground is moving. And again, these are the limits for advanced LIGO, not third generation or any future ones. And we see here very close the coating Brownian motion. This is the Brownian motion, the atomic vibrations due to the coating, the dielectric coating that's put on top of the mirrors to make these test masses be part of the fabry-Perot cavity that measures the fluctuation of the distances. And we also have some other ones like gas in the residual gas in the beam tubes that it's taken very well care of not to increase. and other sources of Brownian motion. So how is it planned to get from here to third generation? Well, with better suspensions, so that passive and more passive and more active cancellation, including cancellation of the Newtonian noise, a longer baseline, because if you have the same fluctuations of the same mirror motion, but you put them 10 times farther apart, then the sensitivity to strain, which is what we have here, will go down. Going underground, because that reduces the seismic noise. So with the same isolation, you get less influence of seismic noise. So there are all these plans, and again, depending on which technologies you use, you get to the third generation curves at low frequencies. In the middle, that's the one more challenging. That's the one that has to do with Brownian motion or thermal noise. And for that, like I said, in advanced LIGO, that is due to the loss on the coating. So if you use mirrors, mirrors are done with coatings. Can you make better coatings? So there are different, instead of the materials that are used now. So there's a lot of research on that. Of course, you could lower the temperature, cryogenics, but that technology also has a lot of other everything needs to be adapted to cryogenics. But also, if you go to lower temperatures, then the loss of the materials, for example, the loss of the fused silica material for the mirror will change. It changes with temperature, and it's not such low loss at low temperature. So you need to find another material for the mirror itself. So it's not trivial, but that is being addressed. There is a lot of R&D needed, but it is being done, and it goes along these lines. And at high frequencies, we are limited by short noise. We will be limited also at low frequencies by quantum noise and radiation pressure. So you could use more power, but then more power just decreases this noise and increases the radiation pressure noise. So you don't want to go down at the cost of going up in another frequency band. So you need to do something else, and that is, for example, make the mirrors heavier, and that decreases the radiation pressure noise. You can do that. But what is being done with that is providing more bang for the buck, if you want, is squeezing. And Eleonora Capocasa will talk a lot more about this. So that is very appropriate for this talk. So this is how you get from this curve for advanced LIGO to the curves that you saw for A+ and third generation, taking into account the projections of the R&Ds, the successful R&D that we will be doing in the following years with the timescale I showed you, to be implemented in those new facilities. However, that's a fundamental noise. Now, how long does it take to get there? And then again, let me take advanced LIGO as an example, and an A+, there's a plus missing in there. So this is the sensitivity of the LIGO Livingston detector. There's a similar plot in this review that we update about once a year. This is a plot of the sensitivity of the Livingston detector in 01, 02, 03. So you can see that we decrease the noise, increase the sensitivity at high frequencies, at low frequencies at different rates. And then there are predictions for 04. Actually, this was not these are a mix of Livingston and Hanford detectors. This is a prediction or an expectation, let's say, for 04 that would start in 2022, mid 2022, depending on progress, which is being slowed down with the pandemic. And this is the expectation with the A+ technology, which is a slight upgrade of advanced LIGO that is going to use lower loss coatings on the mirrors if the research advances to the manufacturing stage, and frequency-dependent squeezing to be able to decrease the noise at high and low frequency. So this is what we want to be sometime, probably not at the beginning of 05, but sometime after. Now you would say that this, and you look at, if you look at the numbers, we started at 80 megaparsecs, while I showed you before the advanced LIGO design curve, and it says new here because in the one that we had in the first paper on advanced LIGO detectors, we had a lower noise for coating, but then new measurements prove that it is a bit higher than we thought. So that's a new in here. And this range for binary neutron star is 173 megaparsecs. But when we turned on in 2015 and we had that great first discovery of the first gravitational wave signal, not from neutron star, but from black holes, our sensitivity was 80 megaparsecs. And that was the best we had, not 175. In fact, in 03, we had 130 and maximum of 140, not 175. So why is it? What does it take to get there? Well, it takes a lot of understanding of the instrument as implemented. So it's not just doing the R&D of the technologies and installing the hardware in place and turning on the switch. It takes a lot more work after that. And this is the state of the understanding of the, again, the noise in the Livingston detector. This is slightly different, but the principles are the same in all the other detectors. Of course, we have in solid lines the fundamental noises, the quantum noise, the thermal noise in all the same colors, the seismic noise. Look at the seismic noise, it's down here. Newtonian noise here, residual gas. At that time, the residual gas was a bit higher, but it's still much, much lower than the measured noise. And why is that? Well, it's because there are all of these other noise sources that are not fundamentals, but they are there. And if you look in here, the noise, the measured noise curves, not the predictions of noises in here, but the measured noise curves are in 01 up here. And that was the 80 megaparsecs. It was a bit less for Livingston. In 02, you see that it's the same at high frequencies because we use the same power, but it is a lot better at low frequencies. And that's because we took a lot more care. And I say we, but I didn't do any of that myself. My students, of course, help with some of that, but this is mostly done by people at the observatories and other people outside the observatory, helping to understand the noise. So this great reduction at low frequencies, which is what made this increase of 80 to 100 megaparsecs, 20 megaparsecs, is due to the taking care of scattered light. That I will talk a little bit more about. Scattered light is light that we use the main laser beam that goes back and forth in the Fabry-Perot cavities, but of course everywhere else. And some of that light is scattered and goes and bounces on something else and comes back to the main beam, but now it comes with information that's not of a gravitational wave, but from this extra path. And that is a terrible noise that's common to many detectors. Actually, I think to all detectors I know about, and that was greatly improved, but not eliminated. From 02 to 03, you see that there was almost no change at low frequencies. It was mostly at high frequencies, and that was due to using more power and squeezing. So we are using now in 03, both LIGO detectors used frequency-independent squeezing. So the squeezing was done in the phase degree of freedom at the cost of amplitude degree of freedom. So there might have been some increased noise in here, but the quantum noise is way below these other noises. But look at how much there is at low frequencies. At low frequencies, if you look in here, the measured noise is the black, well, the sum of the measured noises is the black curve. The blue curve is the actual measured noise. And you see that here, they more or less agree with the prediction, but that prediction is from alignment control. What's that? Alignment control is because these mirrors are hanging in pendulums and they need to be facing each other for the light to go back and forth with the appropriate constructive interference. But if you push on the mirrors to make them face each other as they should, you also introduce noise. And you do that not just with alignment control, but also with controlling other lengths of freedom. So there is excess noise in controlling the interferometer, and we know that's the dominant source of noise. So there is a lot of effort in doing that. But again, these are the sources of noise that are not included in those sensitivity curves, because we know that once you identify them, they can be reduced. But first, they need to be identified, which means that they need time and people and effort in doing that. So that's at low frequencies, but I also want to point in this very rich, information-rich slide that here there is a difference, and in general, this is the case again for most detectors, there is a difference between the blue curve, which is the measured noise, with the black curve, which is the sum of the known noise sources. And this excess noise always happens at low frequencies. It doesn't have a constant amplitude, so we wish this would be an effect of quantum noise or some other fundamental gravity or fundamental physics effect, but it's not. We know that that goes up and down. We suspect that that's nonlinear coupling from other noises, maybe some of these same noises, but identifying the noise is not perfect yet. It will never be, but that's the experimental challenge. That's part of the experimental challenge. So I hope I'm giving you a flavor of how heavy this challenge is. And that's because the detectors are, of course, very, very complex detectors. They are not just Michelson detectors. As you know, we have Fabry-Perot cavities, and David Shoemaker gave an excellent lectures in the workshop in the previous weeks. So I know the slides are posted if you want to look at more details in there. But it's not just an optically complicated detector, because it's a dual recycle with power recycling and signal recycling Fabry-Perot Michelson interferometer. So not only the optical configuration is complex, but all of these little rectangles in here are suspended mirrors. The more complicated are these quadruple suspensions, but all of these mirrors are suspended. And if they are suspended, they need to be controlled. So there are lots and lots of degrees of freedom that need to be controlled without introducing noise. So when we say, well, let's look for better seismic isolation, let's add more stages to the pendulums to get less seismic noise, in principle, all of that is straightforward. In practice, you need to make it work. But again, when you identify the noise, there are ways in correcting that, and that is how you improve the sensitivity. This is an example. For example, I didn't put the reference. I put it when I send updated slides. But this is a way of identifying how pushing on these signal recycling mirrors to keep the signal recycling cavity the way it should be. So again, there needs to be some control signals in here, in there. Those signals are the actual degree of freedom was being sensed by the photodiode that also measures, I will finish in 1 minute. 10, okay. And that includes discussion. Thanks, Luke. And then, and that can be controlled. So in this case, it's not subtracted digitally, which we can do too. And that was done, especially in Hanford, in '02, where there wasn't some noise identified after the fact, but then you can subtract it from the data to produce cleaner data. In this way, in this case, it is subtracted from the signal before it is stored to disk as gravitational wave signal. So it is done in real time. So there are lots of ways of doing this, and that is the challenge. That is part of the challenge. But that's not the only challenge. The second part of the challenge is that you not only want to make this curve lower, you don't want to lower the noise, but you also want to have always the same nice, steady noise, Gaussian noise. So you would, for example, this is the translation of the measured noise curve into a binary neutron star range, and this is averaged once per minute. And in general, and this is a histogram of the binary neutron star range during '03 for Livingston and for Hanford, and it's never the same, it fluctuates, and sometimes it really goes down. Sometimes we just go out of operation, so it's not like it's operating 24 hours, which also matters for coincidence. If you want coincidence data to get sky localization and polarization and so on, you need to have the detectors working more of the time. So when you see these graphs, this is also from this paper that we call Observing Scenario, that shows the progression. This is the progression we had in '01, '02, and '03. These were real numbers. These were measured numbers. Kagra was unfortunately not able to join us, but these were real numbers. And these are projections for '04 and '05. This number is one metric, but we do have variation of that noise. So let me show you some of the details of that. Sometimes we go down. Most of the time, but not always, it's because we have large ground motion and our ways of pushing the mirrors are just not enough to keep them at the right distances. This is the same curve I had before for the noise, for the range at, on March 7 of last year during '03. And this is a measurement of a seismometer filtered at low frequency. So these are not frequencies in the gravitational wave frequency, in the gravitational wave band. These are much, much lower frequencies, but they do affect us, sometimes just taking out us out of log. And then there are times like here where you see that the range is lower and fluctuating a lot more. And that in general has to do with motion also, not in the gravitational wave frequencies, but lower frequencies, but this is in the 1 to 3 hertz, which we call the anthropogenic band, because it's mostly due to humans. In fact, these are most likely trains, and this is probably something else than a train, because it is wider. And then there are glitches, and Katerina talked a lot about this, and I'm glad she did, because there's a lot of these. You see these big drops in the range. Those are due to these monster glitches that she talked about. And the blip glitches, actually, they may be a lower amplitude version of these, so there might happen more often. But here you can see those monster glitches happen quite a bit. And then each point, I didn't explain this, I'm sorry, but in this colorful plot, these yellow dots are all glitches. And the darker the dot is, the larger the SNR. So depending on the SNR, we have lots and lots and lots of glitches. And these in particular are still not as high SNR as the monster glitches, but they are affecting, like she said, these are due to scattered light, and there are more because the detectors are more sensitive. So That's our current experimental challenge. It's to get not just to the 175 megaparsecs, which is what we want for O4, which is the sensitivity of advanced LIGO, but the challenge is now to get to 300 megaparsecs for A+. That is including less noise, less thermal noise, and frequency-dependent squeezing. But the challenge is a lot more than that. It takes a lot of people working on this, a lot of smart people, and I hope you join us because this is fun. And as you will see from these plots that David will use to close the conference, it has a very, very high impact effect. When we get to these sensitivities, we will see the cosmos. Thank you.
Thank you very much, Gabriela, for the very nice talk. And so we take questions now. So let me check the chat. Yes, please, Eric. Eric, you can ask your question.
Thank you. Can you hear me?
Yes.
Okay, very good. Thank you again, Gabi, for the very nice review. I think this was it gives a very nice panorama of the difficulty we have to get there, right? I was wondering whether you have some intuition and anticipation, of course, of whether, you know, from going from where we are now to, you know, the advanced detector, or maybe the third generation detector that we are talking about. Do you think that there may be physics that we have not considered so far, and that do not belong to the fundamental noises that we know limit our sensitivity, but do we expect or do we anticipate some of the difficulty that we did not face so far?
Well, do I expect that?
Yes.
No, I don't think so. But of course, it would be a very nice surprise to find a fundamental limit. You might remember that at some point, there was holographic noise talked about that was limiting the geodetector sensitivity. And this was a noise related to quantization of space-time. And it turns out that when you think about those sources, and some people have thought, there are several papers on predictions of quantum gravity effects on different kinds of detectors, but then it's much better, it would be only seen, I say, in a detector that's built to be sensitive to that kind of noise. So my expectation is that we won't see it because we have not built a detector to be sensitive to that kind of noises. But, you know, I cannot discard the possibility. It might be.
We have a question by Katerina.
Yeah, thanks for the talk. I have a question.
And Katerina, thank you again for filling in for me.
Yeah, no worries. I have a question actually about the glitches. So you mentioned that as the detectors get more sensitive, you have more of those. And is the reason because as you get more sensitive, you see a population of glitches that were quiet, that are quiet now, but won't be quiet tomorrow? Or is it that you add more subsystems and they cause new glitches, or both?
It's both. In fact, we think that that's a cause for the scattering, the really big increase in scattering glitches. That increase was even more drastic in Livingston than Hanford, but Livingston was a bit more sensitive than Hanford in O3, comparing O3 with O2. And when you look at the glitches, the scattering glitches, and you say, well, would this glitch have been noticed in O2, given the noise, the larger noise that there was in O2, they wouldn't have been. So for scattering, for example, these are very, very minute amounts of light that are coming from surfaces. Of course, this has been thought of before, but there are always more surfaces that make light bounce up and down and back and forth. And the smaller amounts of light are not seen unless you have enough sensitivity. So I do predict that as the sensitivity increases, we'll see higher rates of known glitches that have not eliminated and new kinds of glitches that were not noticed before. But there are some other glitches, the ones that I suspect are due, for example, the monster glitches and probably the blip glitches. Those are probably mostly due to the control of the interferometer. And that the complexity gets a bit worse, but that kind of glitches would not necessarily increase with more sensitivity. It could increase with more complexity, but not necessarily with more sensitivity. So it's both.
Thank you.
Thank you. Another question? I don't see other question from the chat. Of no hand raised. I would have a minor point probably. So you distinguish between seismic noise and the Newtonian noise, but obviously the part of the Newtonian noise is due to seismic vibration of the ground. So what is your precise definition between of the two noise with respect to each other?
Yes, that's a good point. There is a definition, there is a distinction, but it's not obvious. The seismic noise and the seismic waves do couple into the motion of the mirror through the suspension path. So the ground moves the suspension cage moves the mirror. That's what we call seismic isolation, is how to prevent that coupling. But now there is also the fact that even if you think about a floating, perfectly floating test mass, the seismic noise will produce different densities on different sides, and there will be Newtonian attraction of the mass, even if you have perfect seismic isolation, and that's what we call Newtonian noise.
So you include into the Newtonian noise also the one which is produced by the seismic?
We don't, we differentiate them. So let me look at that noise budget. Actually, I think this one is better. So the Newtonian noise is this one. And the seismic noise is the brown one. Notice that the brown one decreases a lot more sharply because we have all these suspension stages. Each suspension stage decreases it like 1/f². Here you only have, if you want, one suspension, one connection, which is the Newtonian gravitation, and so it's not as steep. You can make this steeper with more seismic isolation, but you wouldn't change this.
Related to that, there is this alternative to laser interferometry for gravitational wave detection, which is by coupling a series of atomic interferometers. So there is, in France, for instance, there is a MIGA project, other project as well. And so with this technology, you are not sensitive to the seismic noise. However, you are sensitive to the Newtonian noise. So do you agree? What do you think of this alternative technology?
I think it's a very interesting idea. Sometimes I think about the discussion between interferometers and bar detectors at some point. But what I think it's needed is prototypes that have a noise budget like this. What is going to limit the sensitivity? And then a prototype that delivers that sensitivity. That is what was done in LIGO, if you want, with the prototypes in Caltech and MIT, and also with the detector in GEO. You do make a noise budget. You say, we should have this sensitivity, and then deliver it. And as I mentioned, the experimental challenges are not just designing the noise and knowing what to expect, is delivering it. So I think it is very, very interesting, and I can't wait to see noise budgets that agree with measurements.
Yes, they say that they can deal with the Newtonian noise as well, but okay.
Yeah, not just Newtonian noise. Like I said, the experimental challenges are not just the fundamental noises. It's all the rest, like all of these other things.
Yeah. So I am checking the chat if there are other questions or maybe hand raised. Any other question from the audience? Okay, no. So we thank you, Gabriela, again for the nice presentation.